all these things comes into picture. So we have seen in the last class the architecture of microprocessor generalized, and in turn we have seen 8085 is what we introduced. So now what we do, 8086 architecture is what we will see, and then we will go ahead, right? Now, so you can interrupt me. I think you can message me, right? Whenever you have any doubt, so that we can make the class live. Okay, so yeah. So now I'll share my slides. So today's schedule, what we are going to do is we are going to see the architecture of 8086, and we start with 8085 architecture, and then we'll go ahead with 8085 we start, and we'll go towards 8086s, right? So now let me share my slides. Okay, so now, so the last class what we have seen is this, like how microprocessor based systems will look like, and then what are the microprocessor initiated operations, like the functions performed by the microprocessor can be classified into 3 microprocessor initiated operations, internal operations, and externally initiated operations. Under microprocessor initiated operations, you need to identify the memory or IO from where you have to fetch instruction, and once you identify the memory or IO, you have to transfer the data onto the processor, and for that we need data bus. Identifying the memory and IO, we need address bus, and we know that you want to see the sequence and then the control. So control bus is what we needed. So that's what we have seen, and in detail we have seen this, and yeah, this is what the 8086 microprocessor architecture is. So now let us quickly review what exactly we have discussed in the class. So this is what the architecture of 8085. So the memory which we are going to connect is here, and the memory which we are going to connect here depends upon the number of address lines. So the number of address lines are 16, so 2 power 16, which is 64 kilobytes of memory is what we can connect here. So 64 kilobytes of memory is what we are connecting here. So the processor initially will release the address A0 to A7, A8 to A15, and a particular memory location is identified, and that particular instruction through data bus, it will be saved into the registers. So then to save this particular binary data, we need a few registers, like register accumulator is one register A. It is called register A. This is called register B, C, D, E, H, L. So these are general purpose register to hold the data, and then your processor will work, or your processor will execute this instruction. That means this is your instruction decoder, so it will decode the instruction. Based on the decoding, like if you want to add 2 bytes, 1 byte would be in accumulator, 1 byte would be in any one of these registers, another byte would be in any one of the registers. So 8 bits at a time, the ALU, it will perform the operation, either addition or subtraction, right? It will perform multiplication, you cannot do using 8085. Then the state execution can be known by using a register called flag register, And this flag register also in detail we are going to see in 8086. So here there are 6 flag registers are available with 8085. So one flag register is carry, and this is important in gate point of view. 8085 architecture, 8085 microprocessor is there in the syllabus of gate. So at least for that purpose you have to know it. So you have a carry flag, then you have auxiliary carry flag, you have parity flag, and you have sign flag, and you have zero flag. That means, see, we are going in a sequence. Follow me. Here you are connecting your 64 kilobytes of memory. Then any one of the memory location is selected, and that particular data is going through the data bus. It can be stored, it can be decoded by the instruction decoder, and the operands can be stored in the register, accumulator, and this. And once the ALU performs the task, then the status of the task can be known, like you are doing an addition. So then when the addition, when you are doing an 8-bit addition, you have a carry or not, D0, D1, so on up to D7. So 2 bits you are adding. Is there any carries from D7 bit can be known by using this auxiliary carry flag. Carry flag. Carry flag. So this carry flag, if there is a bit generated, means a carry generated from D7, then this carry flag will be set, or otherwise the carry flag will be reset. So this is what the status, this is how you can know the status. And then what is auxiliary carry? When you are doing your binary numbers, or when you are doing your BCD additions, binary coded decimal additions, when you are working on the lower 4 bits, D0, D1, D2, D3, so when you are adding, if there is a carry from D3 to D4, then or otherwise we can say if it is more than 9, you add 6 when you are doing BCD. So that cases we have to know, that case we have to know what exactly, that means how, if there is a carry from D3 to D4 or not. So that particular, when there is a carry from D3 to D4, auxiliary carry flag bit will be set, otherwise it will be reset. Right? And now you are doing addition or subtraction is what I said. When you are doing subtraction, like if all, like when you are doing a subtraction, if all the operation resulted in zeros, then zero flag will be set, otherwise zero flag will be reset. So this is 0, this is carry, this is auxiliary carry flag, the status which you are knowing, right? Then what about the parity flag? This parity flag, when you are doing 8-bit addition, if the result is having even number of ones, then the parity flag is set, otherwise the parity flag is reset. I repeat, when you are doing an addition, if the result is having even number of ones, then you can say like the parity flag is set, otherwise it is reset. And coming to the sign flag, this is an 8-bit microprocessor. Why we are calling it as an 8-bit microprocessor? It has an ALU of 8-bit. It has an ALU of 8-bit. It can do 8-bit. It means the processor can work on 8 bits at a time. So when you are doing 8-bit addition, like there is a carry from, so now let me go through. You have D0, you have D1, D2, so on up to D6 and D7. So now when you are adding or when you are doing a subtraction, the result can be a negative number. So the negative, how do you represent? If the last bit, so the last bit will indicate the number is positive number or negative number. So when there is a carry from D6 to D7, then that number can be treated as a negative number. So then the resultant number is what we can say is negative, and then the sign flag will be set on this occasion, right? So you have 5 flags in 8085. One is carry, auxiliary carry, 0, parity, and side flag. Right? So these flag registers will indicate the status of the operation is, and you can make a decision by checking these particular flags. And once one particular instruction is executed, then the program counter, in the last class we have discussed, the program counter will identify the next memory location and the next byte will be fetched, and then your instruction decoder will decode that particular instruction and your ALU will be performing according to the instruction is. So this is what the architecture of the 8086, how it works. Now, when you are, here, the operation, the execution of operation is sequential. Sequential means what? Now, your processor, in the beginning, it has to fetch the instruction. You have to decode the instruction, and then your ALU will execute the instruction. So, here, decoding and execution. Decoding and execution, these two will happen one after another. So the first thing is you have to fetch the instruction from the memory, then your decoder will decode the instruction, then only your ALU will perform the operation. So this is sequential. So then when it is sequential, then what happens is the processor operations, the execution speed will be getting reduced, or it takes more time, not getting reduced, it takes more time to execute a particular instruction is, right? So now so this is what your 8086 processor, how it works, right? So now so are you with me? Yeah, so are you with me? This is what your how 8085 architecture is. Now we will go ahead with 8086 microprocessor. So now let us try to see. Now let us try to see, this is what the pin diagram. So now you should be very careful in the pin diagram is. So what are all we talked up to now, you should find in. So you have an address lines, and now here to reduce the number of pins, the address lines and data lines are multiplexed. Means what? Same pin can be used. So that means the operations performed by the microprocessor, we can talk with reference to clock. So this is one clock. This is one clock period, right? So in the first clock period of the, so the 8086 works with 5 megahertz. So when it is working with 5 megahertz, then each clock period is 1 by 5. So then roughly you can say around 0.2 microsecond. That means this time period, right? During this time period, the processor will release the address from where it has to fetch instruction. So in the first clock period, this pin number 12 will carry the address 12, 13, 14, 15, 16, 17 and 18 and 19. So these are all 8 pins. Along with this 8, total 16 address lines will carry the address during the first clock period, right? And then in the next clock period, these 8 lines will act like data lines. These 8 pins will act like data lines. This concept is called multiplexing. This concept is called multiplexing. Why it is and what exactly it is? Yeah, same pin is used for two purposes. Right, so that's why it is called the concept. In the during the first clock cycle, the pin will carry the address. During the next clock cycle, the pin will carry the data. So same pin is used to do two tasks. That's why it is called a concept called multiplexing. So what is the advantage of multiplexing? The advantage of the multiplexing is you can use less number of pins. Total pins are 40. I told you in the last class. So there are total 16 address lines. Then there are total 8 address lines. So 24 pins should go for, out of 40, 24 should go for address and data. But now because of the multiplexing, what happens? I can use same 16 lines for carrying data as well as as well as address. So that is what the advantage of multiplexing is. So reduction of number of pins is what you can do with the help of this particular multiplexer, right? And then you have a read bar pin, you have a write bar pin. That means from the processor, when you connect on a memory, if this pin is going low, means the processor is reading data from memory to the processor. Writing means what? The processor is writing into the memory. So this is what the ALE, this is called address latch enable, because the address lines and data lines both are multiplexed. Each concept what we are discussing now is again we will see in 8086 microprocessors. Right, so keep attention and then keep concentration. Right, so each term which we are discussing now, again we will see a few in your 8086 processor. So now this read bar and write bar and ALE. ALE stands for address latch enable. So what is this address latch enable? That means the same lines are carrying address and data. So during the first, that means this ALE will be high during the first clock cycle, and it will latch the address. That means during this, when it is high, the address will be getting separated. How that is and all we will see in 8086. So this is address latch enable. This is what I0 by M bar pin. That means your processor is doing either memory operation or IO operation. If it is low, then the processor is doing memory operation. What do you mean by that? It is fetching from the memory or it is writing into the memory. What do you mean by IO? If you have a floppy disk or pen drive or kind of thing, so it is doing some outside, the data transfer is done for outside devices. So then that is called IO. So it is doing a memory operation or it is doing an IO operation. So that's why, so this is called I0 by M bar pin, right? So these three signals are called control signals. Why control? The data transfer is from memory to the processor or processor to the memory can be seen by these address lines. That's why these are called control lines. Similarly, you have externally initiated signals like interrupt, acknowledgement, this is interrupt request, and these are the hardware interrupts. See, I told you this 8085 is introduced in 1971. Right, 1971. And you have so many, we have seen the evolution. You have like 1971 you have 40, that means 4004. I think 1972 is what your 8085, 74 is what 8086, then 80186, 286, 386, 586 is Pentium, Pentium 1, Pentium 2, Pentium 3, Pentium 4. So Pentium 4 has 32 millions of transistors on it, is what we have seen. And then after Pentium 4 you have now in the era of i3, i4 and i5. That is, those are the processors we are using for our computer. So but meanwhile your Pentium 1, Pentium 2, Pentium 3 and all, they are not there in the market. But whereas if you go and ask in the market, this 8085 microprocessor is still available. Reason is it has 5 hardware interrupts. In industries, to service requests then you can use this INTR, RST is 5.5, 6.5 and 7.5 and trap. So these are the 5 interrupts, 5 hardware interrupts. Hardware means what? Which you can touch. So this is available in the form of a pin, right? So that you can connect your direct interrupt here. So 5 hardware interrupts are there. 5 hardware interrupts are there with this particular microprocessor. That's why it is introduced in 1972. It still exists in the market. That's what you have to understand. So these are the interrupts. This is what your serial input data, serial output data. That means from microprocessor to you want to transmit data certain long distance. So then you will convert that parallel data into serial data, and then you can transmit the data on these 2 pins. So then you have reset pin, and then you have ready pin, and you have hold and hold acknowledge. So what do you mean by this hold and hold acknowledge? In the last class I have discussed. So if you are doing a particular memory operation, then when you are doing a memory operation, you want to transfer your data from your hard disk to your pen drive. So then if processor is involved in it, then it takes a longer time. So then we involve a particular processor called 8237, which is a DMA controller. So it is a DMA. When you are using a DMA controller, then the DMA controller will put up a request like I want to perform the data transfer. So you give your control of your address and data bus. So then the processor will give an acknowledgement with hold acknowledgement. So 823, the DMA controller 8257, the DMA controller gives a request on hold pin, and if it is a valid request, then the processor will access or it grants the permission to use the data buses. Then this 8257 will become master at that time, and at a faster rate will do. This is called DMA, direct memory access, right? Direct memory access. So these 2 pins are that, and every chip has to be given a power supply. So this is VCC, right? And then this is what the ground, and all 40 pins is what we have discussed. So this is X1 and X2, where you can connect your crystal so that you can get a clock. Right, so this is what the hardware details of 8086. Now, the moment you are studying microprocessor, then you are doing both tasks, like hardware tasks and software tasks. Like you are writing a program and controlling device. So you are writing program means you are a software engineer, and then you are controlling the hardware too. So then the moment you want to write any program, then you should know the hardware, right? When you want to design a system, we have seen how the motherboard of your computer is designed around your microprocessor, is what we have seen, right? So then that case, if you want to design a system around the microprocessor, you are keep on connecting different devices. So then you have to know the hardware. So then you want to connect any device, then where exactly you have to connect is what you have to know, and then you have to know the hardware of it. So these are the total 40 pins. This is 0, like 1, 2 pins. If they are left over, we can discuss it. S0 and S1 are status pins, right? So this is what now 8085. So now let us try to see 8085. Now what are the features of 8085? So here in 8085, your multiplexing of address bus and data bus is there. So already I have just discussed what exactly the multiplexing is, using of same pin for 2 purposes. So that is called the multiplexing. And limited speed of addressing. So here the disadvantage, or we can say some features of this 8085, if you see, it has only 16 address lines. So the maximum program you can write is of 64 kilobytes. Right, 64 kilobytes. So the limited speed of addressing capacity, right? So that means it has less number of address lines. So the limited addressing capacity is only there. Then slow speed execution. So why slow speed execution? Just now I have I explained what is that. You have to fetch your instruction, decode the instruction, and execute the instruction. So this will happen in sequentially in 8085. So that's why speed of execution is slow in 8085s, right? Now, then it does not support adequate pipelining. Pipelining means what? This fetching and decoding and execution. If it is done in one clock cycle, then your execution will be very, very fast. So pipelining concept, don't worry, we are going to see this in detail. And lacks of memory pointers such as index register, this is what a point we can say. We can discuss it like it doesn't have any index registers, like index registers to access the memory where your data is stored. This particular thing is not there. So then we can say these are the few limitations of 8085. So why it is limitation? The first point, multiplexing of address bus with data bus. If you have 24 lines, then you can do your 16 lines will carry address, 8 lines will carry data. So then faster, that means speed will not be getting reduced. So this multiplex will be treated as a single disadvantage. So now these are the few limitations. Now we are going to 8086 microprocessor, which is there in our syllabus. Then why we are going means these are the reasons. So these are the limitations, you can say, limitations of 8085. And here there is no multiplication instruction. So there is no multiplication instruction means what? You cannot multiply two 8 bits at a time here in 8085. Why? Or how it can be done? Repeated addition is what we do multiplication. So the moment we need multiplication, we do repeated addition. So that multiplying kind of instruction is not available in 8085. So these are the few limitations of 8085 processor. So that's why we will go for 8086 microprocessors. So be with me. So keep concentration, right? So I'm discussing now. I'm starting from 8085. Then we will go ahead with 8086. Yeah. So now, so these are the objectives. So they are the limitation means somehow we have to overcome. No? So increases the memory addressing capacity is one particular objective. Increases the execution speed and provides powerful instruction set. Functions in multiprocessor environment, and it facilitates programming in high-level languages. So these are the advantages which you are going to get in 8086 microprocessor. How they are, I will come back each and every point. So now let me show you the architecture of 8086. So give a glance. I think in the last class I gave you an introduction. Right, I gave you an introduction of this particular thing. So now let us see. Now, the architecture of the microprocessor is divided into two units. One is bus interface unit and another one is execution unit, EU, and another one is BIU. So what is BIU? Bus interface unit, and another one is execution unit. So like that, see what is had the limitation of 8085 microprocessor. It fetches an instruction and executes an instruction, decodes an instruction and executes the instruction sequentially. So when it is doing in a sequential process, I think I should have somewhere around there. Yeah. So this is what your 8085 is doing. So it is a fetching instruction, executing an instruction, fetching an instruction, executing an instruction, fetching an instruction, executing an instruction in a sequential manner. So when it is doing in sequential manner, then the speed is low, is what we are seeing now. So now what we need to do, we need to increase this, increase the speed of the processor. Increase the speed means what? More number of instructions, if they are executed in less number of clock cycles or clock periods, then we can say speed is more, right? So that's what we are trying to do. So that is done through dividing the whole microprocessor architecture into two units. One is called bus interface unit, another one is called execution unit. So what do you mean by this now? Let us try to see. In BIU, if you try to see, you have an instruction pointer, which we call it as a program counter. And you have some segment registers. Don't worry what they are, we'll try to see. One is core segment, extra segment, stack segment, data segment. Right? So there are the 4 segment registers are there, and one instruction pointer is there, right? Then there is an adder, right? Right, or we can say this is not adder, or we can say, like, you know, it is an, this symbol I told you what, like it is an ALU kind of thing, doing some logical operations, no, arithmetic and logical operations, right? So then this is what your address generation is. So here you have an address bus, and here you have a data bus. In the last class I clearly gave you exactly these things are, right? So here you have an address bus, here you have a data bus. So in 8086, like, you know, you have 20 address lines, and in 8086 you have 16 data lines, right? The total pins, you know, the total pins of 8086 are 40 pins only. It's a 40 pin IC. So 20 plus 16, 36 will go for that. But here we know the concept called what? Multiplexing. So you can use these 20 address lines as data lines too. So that is called multiplexing. So here you have data bus, here you have address bus. Be with me, right? And listen carefully. How, see, our objective is how we are increasing the processor execution speed is what we are trying to see. So the solution is what? Dividing the processor architecture into EU and BIU, bus interface unit. So now, what is the use of bus interface unit, or what is the role of bus interface unit? What is the role of execution unit is what we will try to see now, right? Now, so in that part, we are trying to see what exactly is there now. This bus interface unit will generate the address. What is its task? It has to generate the address from where the processor has to fetch an instruction. I repeat, the BIU's task is to generate the address from where? Okay, from where the microprocessor has to fetch instruction. This is its task. Then the moment I say, so the memory which we connect here is here to the address bus. We connect our memory. So how much memory we can connect here? That depends upon the number of address lines, is what we have said in the last class. Now, how many address lines are there? 20 address lines are there. So what is the memory I can connect to power 20, which is of 1 megabyte. Memory is what we can connect. So then if you connect 1 megabyte of memory, like this is our 0th location, first location, second location, total 10 bar 6 locations are there. So any byte from any memory location need to be fetched. To do that, a particular memory location has to be identified, and that is done by using BIU by generating the address. So this is what address generation and control part. So it will generate the address. So how many bits of address it has to generate? 20-bit address. And we told in the last class, what is the use of program counter? Program counter will point out the next memory location from where the processor has to fetch the instruction, right? Yeah. Then the program counter of the microprocessor 8086 is 16-bit. So if you have 16-bit pointer, then 2 power 16 means 64 kilobytes of memory only it can point. But how much memory we are connecting? We are connecting 1 megabyte memory. Then your instruction pointer or program counter alone cannot hold or cannot point all the memory locations, which are starting from 0, 0, 0, 0 to F, 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 F. This is what I explained in the last class, how you are giving memory locations or addresses to the memory. So to point out this much memory, we need a pointer which is of 20-bit. That means your instruction pointer is of 20-bit. The instruction pointer or the program counter is 16-bit here. Then you cannot address or you cannot add the answer is the total 20-bit address is 086. So with what objective we started? We have to increase the speed of execution, right? So that speed of execution is achieved by dividing the processor architecture into two. One is bus interface unit, another one is execution unit. So this is what we have seen up to now. So this is what the architecture, right? So let me share my thing. Yeah, this monitor. So I'm sharing my monitor now. Yeah, right now, see, yeah, now, so this is what the architecture we are, no, I just know, I think you lost the connection. So now, see, this is what your bus interface unit. So the bus interface unit will generate a 20-bit address. The fundamental task of the BIU is what? To generate address, 20-bit address, right? So now that is done through using this segment registers and instruction pointer. The instruction pointer is of 16-bit, so you cannot access 1 MB location. So that is done with the combination of segment registers and an instruction pointer is what we have said. So this is what your logical and an adder unit where you are adding this particular thing, right? Now, so what is there in your Douglas Hall, the architecture. So this is what your bus interface unit is having, segment registers and then the instruction pointer, which is the program counter, and this is what getting added up. So here you are getting your memory. So connecting your memory from where you have to fetch your instruction, right? So now we will try to see this particular part. What is this particular part? How to generate a 20-bit address is what we will try to see. So now one more difference is like this is what your memory, and in this memory when you write the instructions, like I give a small example, move ax comma bx. That means ax is a 16-bit register, bx is a 16-bit register. This total instruction is of opcode and operand. So this opcode and operand, so opcode and operand is going to be stored in the form of machine, binary level bytes in the memory. So your code and operands are in the same sequence, like it can be here, it can be here. That means your program code and data both are, your program code and data both are in same memory. And what Intel they did in 8086 is all program instructions, your opcode can be stored. Opcode will tell you. So what do you mean by opcode? Opcode will tell you what exactly the processor has to do. What is operand? What operation has to be done on the data is that operand is. So they are stored in the same memory in 8085. In 8086, what they did is the complete code codes code in one memory location, and the data on which you have to perform the task is separated. That is called, so this separation is called segmentation. The separation is called segmentation. The memory is divided. So the memory is divided. So this dividing of the memory is called segmentation, like code segment and data segment. So in code segment, what it will be there? Your program code. And what will be in data segment? Your data. So these two, right? So these different memories are divided into two, code and data. So now the corresponding registers are code segment register and data segment register. Similarly, to point out the stack memory, you have stack segment, and if you have any extra data, then to point out that you have it. So these are the registers. So now let us try to understand how to generate this 20-bit address if you to access your program code. Let us see now, right? So these are the segment registers. You have 16-bit segment registers, right? These are the BIU elements, bus interface unit element, right? So now your code segment register is of 16-bit size and your instruction points are of 16-bit size. And this 16-bit and 16-bit together will generate 20-bit physical address. How that is? Now let us see. Code segment is of 16-bit means this is what the hexadecimal number is, and the last hexadecimal number is this, right? So now, so the total physical address is what the segment address offset address. These two need to be added to get 20-bit address. How that is? Let us see. So this is of 16-bit. This is of also 16. So this is the last address you can hold. Then 20-bit address generation. Now what exactly you are doing is your this 4 left shifted by 4 0 is one particular address. So it is multiplied by 16, which is of of 4 shifts. Shifting leftwards is what, right? So this particular thing, 16 in decimal is of 10, right? So it is multiplied by 10h. That means 4 left shifts is what it will do. So now let us take the code segment is holding a memory location or memory address of 100, and IP is holding an address of 0200, right? So then it is multiplied with the 16, which is of 10h hexadecimal. So when it is left shifted, so then 1000 and 4 zeros will be appended when you do the 4 left shifts. So this is what is done by your BIU unit. It will left shift 4 bits of your code segment content, and your IP content is getting added, right? Added, and total 20-bit address is what generated is. I hope you are following me. So we are discussing about the memory where we have our opcode stored, which we are calling it as code segment. So how to access a location in this particular memory is what holded by CS IP combination. What is CS? Code segment register. What is IP? Instruction pointer register. It is of 16-bit. It is of 16-bit. These two will generate 20-bit address. Of 20-bit address is now let us try to see. So your CS content is multiplied by 16. So this multiplication of 15 is nothing but left shifting by 4 bits. That means appending a 0 on the right. So you are appending a 0 on the right to the content of CS, and your instruction pointer or your program counter, this register is also called program counter, is getting added. So this is your program counter content, this is your instruction, this is your code segment content. These two are getting added, and 20-bit addresses. So this is 1, 2, 3, 4, 5. This is hexadecimal number. Each is of 4. 5 4s are 20. So total 20 binary bit address is what getting generated here in the processor. So this is what. Are you following me? Yeah, is it all right? So this 20-bit address is generated by using this segment register in combination with the instruction pointer, and this is what the left shift, the logical unit is doing the left shift and adding these two, and this is available on the address bus, right? So once a 20-bit address, right, is identified, and from that a byte will be fetched, and this byte is initially saved in a memory locations on the processor, which is we call it as queue. There are 6 bytes you can store: first byte, second byte, third byte, fourth byte, fifth bit, and sixth. So it is first in, first out kind of thing, first in, first out, FIFO kind of thing the queue is. So the first byte will be fetched and then stored in the queue, and then the next address will be pointed out by the program counter in combination with CS, and next memory location is identified, next byte will be fetched and then kept here, and next byte will be kept and fetched here, and next byte will be kept and fetched here. So like that, 6 bytes from 6 consequent memory locations are fetched and then can be saved or passed to instruction queue. Is it all right? Right. So this is what the part of the BIU. I'm sorry, the function of the BIU. What it does, it generates a 20-bit address, and it points out a memory location, and from that memory location that will be passed to queue, right? So this is the function of BIU. And once the data or your opcode or operand is available here, then your E execution unit in which you have decoder and it draws the instruction, right? It draws the instruction from this queue and it executes. Your ALU will execute with the help of registers. So what are there in your EU? So in your EU, general purpose registers are there. What are they? Here you have an accumulator AX. Here you have a register BX, and each register is of 16-bit size. In 8085, each register is of 8-bit size. But here, each register is of 16-bit size. Then this is what the counter register and this is what the data, the name. Accumulator, base register, count register, and then register is. So these are the general purpose registers. And there is a line here which is AL and AH. It is the lower byte of the accumulator and this is the higher byte of the accumulator, AH, AL. It is 8-bit, it is 8-bit, total 16-bit. So these registers you can use it as 8-bit registers, or these registers you can use it as 16-bit registers, or you can use this as an 8-bit, 8-bit. So two individual 8-bit registers you can use, or if you want to use it as a 16-bit register, you can use. Right. So that's why a line is drawn. So the name of these registers are, accumulator, base register, count register, and data register is. Right. And then this is the base pointer. We will try to see the uses of this. And that means destination index, source index, and stack pointer. Already I told you in last class, the moment you want to have, then what do you mean by stack pointer? What do you mean by program counter? What do you mean by these registers? So these are the pointer registers, base pointer and then source pointer. And these are the index registers. So these are index registers and these are the pointer registers. Uses of this is what we will try to see in the next class. Right? So now this EU with the help of registers and then ALU will execute the instruction which is available in the queue. So it draws the opcode, right, from this and it executes the instruction as. Right. So now let me see. So this is what your CS content one example. If your CS is A820 and IP content is this, then what is the resultant physical address? So then what you need to do? So 20-bit addressing A820 has to be multiplied with 16. So then we can say 4-bit shifts. Like A is what? 1010, 8 is what? 1000, and 20010, 0000. This is what 16-bit. So 4-bit shift left. So that is the same. So then here you have A820 multiplied. So A0 will be appended in the last. And then here you have 0CE24. So these two has to be added to generate a 20-bit address. So 0 and 4 and then 0 and 2 and E is, so E2 na. So E2 means here E is what? 15 na. 0 A B C D E F. So this is 9 9, 10, 11, 12, 13, 14. So E is 14. So E is 14 plus 2, 16. So 16 means what? Now, so this is 14 plus 2, 16. So 14, 15 and 16. So 16 is 0. So here you have 0 and a carry. And 8 plus C. So C is how much? 12 plus 8, 20. So 20 means it's already 15, 16, 17, 18, 19, 20. So this is a 4 and a carry. Right. So A is what? 10 plus 1, 11. So 11 is what? B. So this is what the physical address is. If CS contains 0A820 and your IP contains 0CE2, then the physical address is this. Similarly, you can go through this. If CS content is this and IP content is this, then what is the physical address is what you can go ahead is. Right? So now, overall, to see what is the advantage of dividing the architecture into BIU and EU. Let us see now. Your BIU task is fetching an instruction, fetching an instruction, fetching an instruction, and passing into queue, passing into queue, passing into queue. So your queue is filled with all instructions. So your fetching operation is done in one particular clock cycle. Right. So this is in clock cycle. So in first instruction, like in a first clock cycle, take your first instruction is there in first byte. Assuming in first byte, in a first clock, no instruction is in queue. From second instruction, from the second clock, this is first clock, this is second clock. So in first clock, your BIU will fetch the instruction and pass into queue. And in second clock, it fetches the next instruction and it passed into the second queue. In second clock. Meanwhile, EU will draw the instruction from this byte. So in second clock, fetching and execution done in one clock cycle. Are you following me? Now, so in third clock cycle, it fills the third byte in third queue. Is what fetched by your EU. EU draws the second instruction and it executes. Right? So this within a clock cycle, fetching and execution will be done. This is called overlapping. This is called overlapping of fetching and execution. It is called a concept called pipelining. It is a concept called pipelining. Fetching an instruction and execution of instruction happens in one clock cycle. In 8085, what happens? In one clock cycle, it will fetch. In another clock cycle, it will execute. In next clock cycle, it will fetch. Next clock cycle, it will execute. So that means one byte instruction execution takes 4 clock cycles. But here, one within a clock cycle, within third clock cycle, your fetching and execution will continuously be done. So this is what the advantage of, right? This is what the advantage of this particular architecture is. So this is what your 8086 architecture, which is divided into two. One is bus interface unit and another one is execution unit. Are you following me? Yeah. So that's why it is divided into two. And this is how we can increase the execution speed of the processors. It is divided into two. One is BIU and another one is execution unit. What is the function of BIU? BIU will generate 20 and it will fills the queue. And EU will draws the instruction from the queue and it executes the instructions. So fetching and execution happens in one clock cycle. The concept is called, because usage of dividing our architecture into two results in a concept called pipeline. So this is one stage of pipeline. Your Pentium 4, your Pentium processors will have 4 stages of pipeline. We are talking about one stage of pipeline. Okay, so you may be having a question, sir. We are studying a processor which is invented in 1974 when we are using i3, i4, i5 processors now. Then what I told you, if you understand this 8086, a lesser computation, lesser complex processor, you can understand the other processors too, right? So be careful, while you are doing this. So they were ELU. To ELU, you should have flag registers. What are the flag registers? Why you use flag registers? To know the status of your operation. You are doing an addition, whether there is a carry or not. Somebody should indicate. So that is done by using your flag register is. So this is what the architecture is. So this is what your flag and your ALU, and this is what your address bus, and then here this is what your internal thing, and then your 8086 how the architecture of this 8086 is. So this is what we have seen. So the fetching and execution is done in one clock cycle, and that's why and that is how pipelining concept is introduced in your, so pipelining concept is introduced in your 8086. So there are star marks. What do you mean by this? Now here you have how many bytes queue? 6 bytes queue. If this queue, if any one of the byte is not drawn by EU, this queue is filled. When this queue is filled, then your BIU should suspend the fetching instruction. If it is fetching instruction, means it will be overwritten in the queue. So that is why let us consider few cases when BIU will suspend its operations. Let us see. Is it all right? Right. So that is what it is marked here with star mark. So that means when you have an instruction called AAM with 8086. What do you mean by this AAM? ASCII adjust after multiplication. That means you are doing 216-bit multiplication, but after doing it, adjust that into ASCII code. This instruction takes 84 clock cycles. So that means one instruction, when it is executing, 84, the EU will take 84 clock cycles to execute this particular instruction. Then when EU is doing this particular task, only six clock cycles are needed for the BIU to fill this. But 84 clock cycles, this EU is engaged. It will not draw instruction from EU. So then what BIU has to do? It has to wait. It has to wait until it performs a particular task, right? So when longer instructions your EU is executing, the BIU will suspend the operations, right? So like instruction AM, like instruction DAA, decimal adjust after addition, right? And then you have an instruction called call. You are calling a subroutine from somewhere. In that case also, it takes longer clock cycles, and then your BIU has to suspend. So that is shown with these things. So when EU is executing longer clock cycle instructions, BIU has to suspend its operation. So then again, it has to, from where it stopped, there onwards, then this has to be overwritten, right? So again, it has to perform the same tasks. So this is what, so there are three conditions in which the BIU will suspend. The first occurs when instruction requires access to memory location not in the queue. This is the first reason. Yeah, that means what? Now you are calling. See, now you are executing instruction which is there in the memory, but your operand will be there somewhere in the memory. So, but your operand is not available in the queue. So then what the processor has to do? The processor has to fetch the byte which is there somewhere, and that byte now has to be passed to EU. So then all these operands again need to return. So that is the first case. Your BIU will suspend its operation. And when instruction is instruction, so jump means jumping one place to the another place. Like you are executing in sequence all the instruction, like add 2 bytes, then see. So jump on carry. So jump on carry somewhere. So that is not in the sequence. So then what you do? Again, you need to go to that particular bytes and then fetch. In that case, BIU will suspend the operation. Then the third one is long, suspend fetching instruction that occurs when execution slow is, slow executing instruction. This is what we have discussed in thoroughly. So now all these three cases, your BIU will suspend operation. I repeat. So when the instruction is requires access to memory location not in queue, and when there is a possibility of jump instruction and long execution instructions, when you are going for these three cases, which are the with star mark, then that case you have to rewrite your bytes in a queue, right? So uses of registers now is clear now, and so far what we have discussed. Let me see how much things, how much content we have discussed. So is that all right? Why the architecture is divided into right? Why the architecture is divided into different parts? Is it all right? Okay. How the processor, what is the use of the processor is, right? Now let us see the other components which are there, okay, which are there in the architecture, right? So now let us see the architecture. What are the uses of these general registers? What are the general purpose registers are there? Accumulator, base register, counter, and data register. So these are called general purpose, pointer registers, and index registers. So these are index registers. Right? So then how to know of all these things? So like we divide them into data group, pointer and index group, status control group, and segment group. This is how you can discuss. So now, as time time is not there now, let us review me. So today what we discussed, okay, today what we have discussed is, right, so we have seen the architecture of 8086 processor in detail, and then we have seen the architecture of 8086 and how we are making or how we are improving the performance of the processor by dividing the architecture into two: bus interface unit and execution unit, and how 20-bit address is generated by using DIU, and the working of 8086 processor is what we understood, and the register group is need to be discussed in detail, and it is very important in programming point of view. So in the programming point of view, we'll try to see this particular registers in detail in the next classes. Okay. So if you have any question, then you can ask me, and we'll meet in the next classes.